Good morning, Eastview Chemistry fans. We are back again. I'm here with my trusty lab assistant over my shoulder, and this is part two, day two of the reaction rate lab. Yesterday, of course, we did part one, and that was a concentration sample. We have learned and seen in demonstrations that there are four factors that we really look at for changing concentration. Changing reaction rate. Concentration we did yesterday. And we worked on different concentrations of a couple different substances, and we'll be analyzing how that affects the reaction rate in relation to what we've learned in class. Catalyst and surface area are two things that we showed you in the demo. They're not going to be essentially part of this lab at this point. We're just going to keep it to a couple of the factors to get lab data, but certainly those are ways to increase, or other than the catalyst, you can also decrease your reaction rate if need be. Remember, catalysts only increase. The factor we're going to look at today in part two is temperature. And so if you notice at your data table, yesterday, the only thing that was consistent throughout every experiment was the volume of what we've labeled letter B, the sodium thiosulfate. And then what we did is at some points we kept the potassium iodide constant while we varied the ammonium persulfate. And at times we kept the ammonium persulfate constant while we varied the potassium iodide. Today, if you look at the table, all as a control measure, all the volumes are going to stay consistent of all the chemicals. And really what we're going to do is test them at different temperatures. Right over my shoulder, you can kind of see it over by my assistant there. I have a hot bath. Right behind me, I have a cold bath. And so what we'll be doing off camera when we pause as I set up each lab is I'll just be taking those amounts. I have some test tubes here labeled A, B, C. I'll get the appropriate amounts in the test tubes and then hold them either in the cold bath or the warm bath till they get to temperature with my thermometer. And then we'll have the reaction going. You'll see that part. We'll get the reaction going and you'll be able to follow that part. And so we'll collect, again, time data on how the temperature changes will affect the reaction rate. And then all this stuff, both from part one, part two, and how we're going to analyze those and use those, we'll discuss in our next video. Anyhow, I'm set up and I'm going to jump right into the middle of the table and what's labeled here as room temperature, which is right now 20 degrees Celsius by the thermometer. So that is labeled lab number 10 right now here, mixture number 10 in the deal. And I've got it all set up, and now this one I don't need the test tubes for because it's at room temperature. Once again, just like yesterday, B is going to go in, and then I'm going to simultaneously put in A and C and hit my timer and then start stirring and wait for it to turn its dark color. So here we go, in we go, dump it out, timer on, and I'm going to stir away. And again, this is day two of exciting, thrilling stuff for you, where you get to watch me stir until the color changes. If I have done this right, and if it follows what I did in a little testing before we started filming, we want to be around a minute, maybe a little over. As if you think about it, if you think of what we've learned already, as we go to the higher temperatures, the reaction should go faster. And we want to have some time for the reaction to have that ability to change. Remember, yesterday when we were doing concentration, we had the full-on 10, 10, and 5 milliliters of each of the substance landing about 30 seconds. And that would not, under heat condition, give us almost enough time to measure it. It would be so rapid. So here we go. And there we go. We are at 70 seconds right on. So I like that. That's good. So our room temperature, 20 degrees, was 70 seconds. I'm going to pause for a minute and set up the next reaction, and we'll be back. So stay tuned for the excitement. Okay, we're back. All right, so here's what I've done, and I need to grab my stuff here. I held these, we're at the 5 degree. Here's B. I held these in the ice bath until they all reach 5 degrees. And now we're going to just do the same thing. We're going to mix A and C at the same time. I just put B in. We're going to hit the timer and again see how long it takes for this stuff to get going. Timer on. I'm going to start stirring. Kind of like yesterday, if it looks like it's going to go, you know, more than 5 minutes, we may end up pausing and coming back with the time on it. Theoretically, as we watch this, let's see, room temperature was about 70 seconds, so we hope that this takes longer. We have cooled it down. The energy level of the reactants should be lower, less kinetic energy, which means less chance of colliding. There'll be, of course, it'll be moving slower. They'll be colliding with less energy. That decreases the chance, as we talked about activation energy, that they will collide with the appropriate energy and orientation for the reaction to occur. And that's what will make the rate go slower. In theory, I'll be happy when I know we're past 70 seconds. Okay, good. We're passing 70 seconds, so I haven't goofed it up so far. So far, I'm not being a lab doofus. I know, can you stand the excitement? It doesn't get any better than this. We're at 2 minutes. I'll give you a question to ponder while we do this. I threw this out at my physiology students yesterday. What is the current most popular thing going on that annoys the heck out of you? I can't remember what I said, but whatever I said something, and they said, oh my goodness, that's 2 or 3 years old. You're way past the time. Oh, here we go. 2:37. 2 minutes, 37 seconds for the 5 degree. Oh, I know what it was. I told them fidget spinners, and they said I'm way behind the times because, you know, it's more than 6 months old. Anyhow, I'm going to pause, clean up, and we're going to come back with our next mixture. Okay, we're back. And now I have taken our stuff. Let me get B in there. And this is the 15 degree mark. So I held it in the bath until we were at 15 degrees. And again, we're going to dump and stir. Hit the timer. Stir it. Now, our room temperature, 20 degrees, was 70 seconds. And our 5 degree was 2:37. So we're at 1:10 versus 2:30. This will hopefully be somewhere in between. You certainly feel free to make a guess, but again, no wagering, ever. Illegal. Again, why should it be slower than room temperature? Less kinetic energy. Less chance of colliding at activation energy. And of course, improper orientation is always involved in there also. Okay, we're past 70 seconds. And bam, 150. 1 minute, 50 seconds. Write that down. Okay, pause time. We'll be back with higher temperatures. Okay, we're back. We're at the 35-degree mark. I want to get things going before they cool down too much. There's my B. There's my A and C. There's my timer. We assume this is going to be faster than 70 seconds. Again, why? Because it's at a higher temperature, higher kinetic energy. More energy, more movement, more faster, more collisions at the appropriate energy level, and orientation. We love reaction rate stuff. We hope we love it. We hope it goes faster. And there we go, 47 seconds, bam. 47. We have one more to go. We have the 45-degree stuff. I'll be back. I'll be back. Okay, we're back. We're at the 45-degree extravaganza again before it cools off too much. There goes my B. Here's my A and C. Bam. Timer stir. What do we want to beat? We want to beat 47 seconds. Again, higher kinetic energy. Bam. We were at 10 seconds. Woo. That's speedy. Okay. So 10 seconds. So at least at a minimum, between yesterday and today, yesterday with concentration, you saw that as things got more dilute, either with A or with B, that the time extended because you didn't have the concentration as the full-on 10 milliliters, less particles, less collision, less opportunity to reach activation, energy, and orientation. Today, starting from our baseline room temperature at 20 degrees, you saw that as things got colder, it took longer. Less kinetic energy, less chance to reach, it's all that collision theory stuff. And then as we got warmer, it went faster. Again, collision theory, more energy, more collisions, more opportunities happening at activation energy. Anyhow, thanks for watching. Tomorrow we'll go over the analysis and what's expected in the whole lab and in turning it in, etc. But until then, stay safe and don't do too many bad teenage things. We will talk to you soon.